Good morning, everyone. We come to you today with a question that worried us and that you've probably made yourself once or another. How good are my paleodiversity measurements? Or in other words, have I recorded have I a good picture of the paleodiversity of a given bed or a given locality? And if not, how much effort should I do to reach this good measurement of paleodiversity? Although this is probably frequent questions in paleontologists' mind, there are scarce examples of addressing these kind of questions within publications. For instance, in the paleobotany domain, in which I developed my career, it's frequent to see publications in which lists of taxa are described, but very often how these taxa are distributed within beds or in some samples of the bed is not often detailed, and so inference about their spatial or the temporal distribution within these beds or within these samples is not possible. And another associated problem is that a measurement of how representative the described richness is not often given. I thought it was a particular case of paleobotany, but apparently this is a general critical issue in paleoecology. There's a group of paleoecology specialists, American specialists, that have discussed this within a symposium for several days, and that resulted in a publication by Bennington and allies in 2009. So these authors have suggested that maybe using similar methods to those they use in ecology can help improving the paleodiversity acquisition process, increase comparability between paleoecological data, and allow the integration of paleoecological and ecological data. We want to draw your attention today towards one of the most used methods to monitor paleodiversity acquisition process, which is the clenched equation. The clenched equation is normally used to evaluate the completeness of a paleodiversity dataset as a function of the sampling effort it's made. So here you see the equation. In the practice, what we do is measuring the richness of several samples, and we estimate the average cumulated richness as a function of the addition of samples by randomizing the order of samples to remove any possible effect of the order of sample addition. So we can take this measurement of accumulated richness within the equation and relate it to the number of samples we've measured to estimate a parameter A, which is the taxon addition rate, and a parameter B, which is the shape of the curve in the last stages related to this taxa addition. And from these two parameters, we can estimate the curve slope at these last stages, which is a measure of stability of the estimates produced by the model, an estimate of the total richness of the sample we are measuring, the proportion of the richness we have recorded for a given sampling effort, and the number of samples we would have to sample to reach a Q proportion of the richness of the total richness of the sample. So we think this kind of equation can be very useful in paleontology because it allows to evaluate the trade-off between loss of information and the amount of work to be made. Generally, in the neoecological studies that have been made using this kind of methodology, we estimate that we have reliable estimates for curve slope values lower than 0.1 and recorded richness higher than 70% of the total richness. So we've applied this method to the study of the plant diversity of the lower Cretaceous locality of Autrage in Belgium. And we have divided our work in two stages. One first stage, bird and experimental design, considering two experimental units within the sampling universe of Autrage, which represent two beds in which we made systematic sampling, taking 8 samples per bed, spaced by 3 meters, once from each other. And each sample comprised 10 liters of bulk sediment. Each sample was separately treated, transported, stored, and soaked within a water bath or a very diluted bath of hydrogen peroxide. And then the sediment was rinsed through a column of sieves with water. And the resultant, this was to separate plant remains from the sediment. And we left the plant remains dry at room temperature, and so we could analyze it under the stir microscope. So from the resultant material for every sample, we randomly took several 0.5 gram replicates, and the number of replicates was taken to fulfill requirements of a curve slope value under 0.1 and a value of recorded richness higher than 90%. And all this work was really, really funny until the moment we realized that each replicate meant identifying about 100 remains of plants, but it was the effort. So here you can see two figures representing the results obtained for the two beds. Vertical bars represent the richness we obtained for every lateral sample. So 90% of the richness for each sample, and the numbers in orange represent the number of replicates that were needed to attain this percentage of recorded richness. So as you can see, we found marked differences between lateral samples, both in richness and in the number of samples that needed to be processed. So all this means that when dealing with fossil paleocommunities such as plants that are potentially heterogeneous, it is needed to consider several lateral samples to have a good view of the total diversity of the locality. That using a subsampling method in each lateral sample allows considering every lateral sample as an independent sample from the statistically point of view, and so we can really robustly measure the spatial distribution of this diversity, and that it's more important to look for an homogeneous representativeness of diversity than having a homogeneous sample size between samples. We took in consideration these conclusions to study the plant community patterns in 12 beds of the Autrage series. So in the first stage, we analyzed the spatial and temporal patterns of this paleocommunity of diversity to look for taxon association patterns. So here you can see the output of a non-metric multidimensional scaling showing the recurrent association in space and time of fern and conifer taxa such as Leicanites and Paiophyllum Arctopithys and Phlebopteris, and Sphenopteris with the conifers Elatides and a new conifer type. We also found marked differences between beds with regards to richness and vegetation maturity. And we use this data to reconstruct the evolution of the plant community through the Autrage series from these 12 beds. And apparently we found that wildfires were really important in the evolution of the community dynamics. Here you can see early to late successional stages of the plant community from green, light green to dark green. And to finish, what is in for you? Because I talk about a particular case, but the important thing is that the clenched equation can be used in any fossil type or size. And the only difficult part is developing an appropriate experimental design and the difficulties of structuring fossils. But you already have this problem. So and the use of this equation provides a measurement of robustness of the taxonomic inventories by saving time and money if you use this kind of methodology in the field, and by adjusting the effort needed to be made. And this kind of methodology can help finding better signals of paleoecological patterns and processes. I hope you'll find it useful. Thanks for your attention.